we're going to continue our conversation on proportions. And now, in the same way that we looked at the sampling distribution of the mean in our previous lectures in chapter 8, now we're going to look at the sampling distribution of the proportion. We're comfortable now with what a sampling distribution is. It's just now I'm changing the statistic. So rather than looking at the sampling distribution of the mean X bar, we're going to now investigate the sampling distribution of the proportion P hat. And remember, a sampling distribution is just a probability distribution, which lists all the possible values of the sample statistic, which in this case now is going to be the sample proportions, the P hats, of the same sample size selected from a population, along with the probability associated with each value of the sample proportion. So very similar to what we did in that very first example a couple of lectures ago, when I gave you that population of test scores and we took samples of size 2 and we looked at the sample mean X bar for every single sample and we formed the sampling distribution of the mean, we could do the same thing with sample proportions. So rather than going through another whole example where I demonstrate, by making a table and taking all samples of size n and compiling all the different p hats, I'm just going to cut to the definitions of the mean and the standard deviation of the sampling distribution of the proportion, since we did something very similar with the means. So if I were to look at the sampling distribution of the proportion, we could calculate the mean of the sampling distribution of the proportion. And we denote the mean of all the sample proportions as mu sub p hat. Just like when we were talking about means, the mean of all the sample means was mu sub x bar. Now we're going to use the symbol mu sub p hat. And let me make this a little bigger. And mu sub p hat is equal to p, the population proportion. The standard deviation of the sampling distribution of the proportion, or the standard error of the proportion, is denoted by sigma sub p hat. So very similar notation, except instead of x bar, we're working with p hats. And the standard error of the proportion, or sigma sub p hat, is going to be calculated by taking the square root of p times 1 minus p divided by n. And just like we had sampling error of the mean, we're also going to have sampling error of the proportion. So p hat is used to estimate p, the population proportion. But like I said, most of the time, it's not realistic that we're going to have data from the entire population. So we would never be able to calculate the population proportion. Instead, we would take a sample and we could calculate the sample proportion and use that as an estimate of the population proportion. So we use p hat as an estimate. Oops, sorry, I'm trying to change this. We use p hat as an estimate of the population proportion p. But most likely p hat, the proportion that we get from the sample, is not going to be equal to the true population of the proportion. There's going to be sampling error. So again, sampling error is inevitable. And the difference between p hat and p is sampling error of the proportion. So what I want to do in the next two examples, 15 and 16, is let's practice using the definition of the mean of all the proportions, mu sub p hat, and the standard error of the proportion, sigma sub p hat. So let's look at example 15. A national caterer determined that 87% of the people who sampled their food said that it was delicious. A random sample of 144 people is obtained. The 144 people are asked to sample the caterer's food. If p hat is the sample proportion saying that the food is delicious, what is the mean and standard deviation of the sampling distribution of p hat? So this is what's going on here. Imagine we know that of the population of people that have tasted this caterer's food, 87% say that it's delicious. That's the population proportion of people that say that this food is delicious. So 87% or 0.87 if I write it as a decimal. So that's the population proportion. Now what we're going to do is we're going to take a random sample of 144 people. So we're going to grab n equals 144 people. And we're going to say, okay, taste this caterer's food. P hat is going to be the sample proportion saying that the food is delicious. So my question is, what is the mean and the standard deviation of all the P hats? So in other words, for every possible sample of 144 people, imagine measuring the percent or the proportion P hat that said the food is delicious. For every single different sample of 144 people, we're going to have a different P hat, a different proportion that says, yes, the food is delicious. If I were to take the mean of all those P hats and the standard deviation of all those P hats, what would they be equal to? That's what I'm asking. So what is mu? Oh, let me change that. Sorry. What is mu sub P hat equal to? And what is sigma sub P hat equal to? So mu sub P hat is always going to be equal to P, which is the population proportion. And in this case, we were told that P is 87% or 0.87. So the mean of all the sample proportions is equal to 0.87, which is just P. The way we get the standard error is this definition above. We take the square root of P, the population proportion, times 1 minus P divided by N. So this is going to be the square root of P times 1 minus P divided by N. So this is going to be the square root of 0.87 divided times 1 minus P, which is 0.87. And we're dividing that by N, which is 144. And that we have to plug into the calculator. So let's plug that into the calculator. Let me share my calculator. So pull up your square root. And we're going to do, I like to put parentheses around the whole numerator. So whenever I write a fraction, I like to put parentheses in the numerator just so I make sure that the order of operations doesn't get messed up. So I'm going to do parenthesis for the numerator now 0.87 times 1 minus 0.87, close the parenthesis. That's for the 1 minus 0.87. That's for multiplication. Now close the parenthesis. That's for the numerator. And we're dividing that product by 144. And we get about 0.0280. So this is equal to 0.0280. So that's how we calculate the mean and the standard error now of all the P hats. If P hat's my random variable, if I'm interested in the sampling distribution of P hat, the sample proportion. Let's do one more example. So example 16 reads, a greenhouse in a tri-county area has kept track of its customers for the last several years and has determined that 28% of its customers plant a vegetable garden in the spring. The greenhouse obtains a random sample of 1,000 of its customers. What is the mean and standard deviation of the sampling distribution of P hat, which is the sample proportion of customers that plant a vegetable garden in the spring? So very similar question to the one above. So we're looking at a population. So our population here is all customers of this greenhouse. And it's been determined over the years that 28% of its customers plant a vegetable garden in the spring. That 28% is a proportion. It's 28% out of 100% plant a vegetable garden. So we're being told that P, the population proportion that plant a vegetable garden, is equal to 28% or 0.28. Now imagine we take a random sample of 1,000 customers. So we're going to take n equals 1,000 customers. Fix that. What is the mean and standard deviation of the sampling distribution of p hat? So imagine it was possible that we took all the possible random samples of 1,000 from this population of customers. And from each sample of 1,000, we measured p hat, which is the proportion that plant a vegetable garden in the spring. What would the mean of all those p hats be? What would the standard deviation of all those p hats be? That's what I'm asking. So what's mu sub p hat? What's sigma sub p hat? Mu sub p hat is equal to p, the population proportion, which is 0.28 in this case. And sigma sub p hat, like we did above, is equal to the square root of p times 1 minus p divided by n. So if we plug in, we're going to have the square root of 0.28 times 1 minus 0.28, and we're going to divide by n, which is 1,000. And anytime we calculate the standard error, I like to go 4 places. So I want you guys to plug this into the calculator. So we're doing 0.28 times 1 minus 0.28. And then we're dividing that by 1,000. And we're getting 0.0142. And just to make sure you guys are plugging that in correctly into the calculator, if you're not getting that, let me show you. Pull up your square root. Open a set of parentheses. Let's put the numerator in. So we're going to do 0.28 times 1 minus 0.28. Close the parenthesis for multiplication. Now close the parenthesis for the numerator. And let's divide that by 1,000. And you should get 0.0142. So that's where that's coming from. So that's how we calculate the mean and the standard error of the sampling distribution of p hat. Now, remember back to what we were doing when we were looking at the sampling distribution of the mean. When we were describing it, not only were we describing the mean and the standard error, but we were also describing its shape, right? For x bar, we like to get the shape of x bar, the mean of x bar, the standard error of x bar. We're going to do the same thing for p hat. So in the next lecture, we're going to talk about how we determine the shape of the sampling distribution of p hat.